So, let's begin. Or let's continue. Where were we? We had a generating functional. We had the initial conditions. We were about to work out the initial conditions. And let me briefly summarize approximately how far we were. So, that we can write our generating functional for the entire system of particles in this way. It's an integral over the initial conditions. That's the this integral measure d gamma here. And then we have a phase factor containing the scalar product between the source field J and the entire bundle of particle trajectories x bar. And the understanding was that, first of all, x bar is given by the initial positions of the particles in, I'm not going to leave, the initial position of the particles in phase space times the Green's function, and then some force acting on the particles that we will deal with later. and contains the Green's function, contains the force term, and so on. The scalar product here contains a time integral, right? Because both x bar, both x, like a snake, I'm happy it doesn't move on its own. Not for me. Given by a Gaussian distribution. So this would be, in very shorthand notation, dq, that's an integral over all particle positions, dp, integral over all particle momenta. And then we had a Gaussian distribution, essentially a Gaussian distribution, for the momenta. All right. There was an approximation going into this. Essentially, we are taking into account that momenta are correlated, but not with particle position. And this is because the momenta will turn out to be much more important for structural formation than the initial positions. So we have a flat distribution in space, and we have a Gaussian distribution momenta. That's an approximation, and if you want to work out, or if for some reason you find a problem sheet where you need to work this out, then you would see how you would take into account the density fluctuation. All right. So essentially, we have everything we need. We have a Green's function from before. We have the Gaussian distribution for the momenta. We just need to work out what are these matrices, right? Or what is this matrix CPP? And there, we had already calculated last time that we can write it like this. CPJ dk. So this is meant to be the correlation between the momentum at particle position J and the momentum at particle position K. Right? So these are two vectors that we have to cross-correlate. So the complete correlation function is a 3×3 matrix. We saw how we would calculate this. So this would be the gradient of the velocity potential taken at position J times the gradient of the velocity potential taken at position K, averaged over realized section. 3×3 matrix. And then we saw last time that, first of all, this turns into an integral that contains, among other things, the tensor product between the two wave vectors K. And it contains a Fourier factor here, and R is the relative coordinate of the particle K relative to particle J. But we have to integrate over all K here. And this means that the orientation information contained in the vector K is lost. And there is only one vector, namely the vector R, which can give this matrix here any kind, its principal axis, can assign an orientation to this matrix. And so we decided to split this matrix into projections with respect to the direction R and not with respect to the direction K. So we said, okay, we are going to introduce a parallel projector P parallel. And parallel means parallel to the direction r, and r hat is the unit vector into direction r. So that's first of all a projector because pi square parallel equals pi parallel, right? And any operation which squares to itself is a projector. So it's a projector. It's parallel to r because for any vector, it would project the component of this vector parallel to r out of the vector. All right. Likewise, we had the perpendicular projector, which was just the complement to the parallel projector. And then we said, all right, we are going to project the matrix CPJPK on the projector P parallel in terms of a scalar product for symmetric matrices that we had defined before. And so we had introduced a scalar product for matrices like this. That's for square matrices. If the matrix, sorry, for symmetric matrices, the matrices are not symmetric. You transpose the first factor. So we had introduced a scalar product, and then you do exactly the same as you would do for vectors. Right? You project on a basis element, and then you multiply with this basis element. Okay, so we had this. Same thing we did with pi perpendicular. Gives you something. Gives you another thing. And then you can work out, and we did this last time, and I don't want to repeat this in all detail. You find that this is some function a1 of q, and q is the length of the separation vector here. Let's write a1 of r times the unit matrix in 3 dimensions minus a2 of r times the parallel projector. That is the final result after doing all these steps that I described and that I carried out last time. And the function a1 of r is defined to be 1 over 2 pi square integral from 0 to infinity pk p delta of k times j1 of kr divided by kr. And the little j1 was the spherical Bessel function of first order and first kind. And for a2 of r, we had 1 over 2 pi square integral 0 to infinity k p delta of k j2 of k. Bessel function, spherical Bessel function, first kind, second order, so on. So that was the result. Of last time. And of course, there are other correlation functions as well, correlation function for the density, correlation function between density and momenta, and so on. But because of our original approximation that we only take the momentum correlations into account, we don't care about these things. So for the moment, this is the main result of calculating these correlation matrices, or that correlation matrix. And you see that once you know the power spectrum of the density fluctuations, which in cosmology we do believe we know very well, then you can calculate these functions and everything. So far, so good. Do you have questions up to this point? Well, fine. I should say right in the beginning, for large values of k, or large values of r, these Bessel functions oscillate like hell. And then you have to integrate over or very rapidly oscillating functions, then you have a hard time, or your computer has a very hard time. Nonetheless, right? Okay. Now we have approximately everything we need. Right? We have the initial conditions. We know how to calculate this matrix there. We know the Green's functions. We could start doing what? What exactly do we want to know? Ultimately, we want to know correlation functions. That's the complete business we are going to pursue. So we need correlation functions between density fluctuations, velocity fluctuations, and so on. So let me first talk about density fluctuations. So I want to know something like, what is the density at one point and one time? Let me just briefly write this as a row of 1. Density fluctuations, or density at another point, so on and so forth. I want to know correlation functions of this sort. Mostly we will have to do with so-called power spectra, so correlation functions of second order, right? 2-point correlation functions in Fourier space. But this is the main business we are pursuing, right? What are correlation functions for cosmological fluctuations, density fluctuations, velocity fluctuations, and so forth. And I'm going to abbreviate this as G of 1 to R. So how do we get this? Well, these are averages over quantities, and by its derivation, you know that the probability distribution for any final state of the complete particle ensemble is contained in the generating function. So what we have to do in order to calculate this is that we would have to integrate over the complete freedom we still have. This is the integral over the initial conditions times the probability distribution for any final state, right, times these densities. But by the definition of our generating functional, this just corresponds to the following operation. Or this just corresponds to an operation to be applied to the generating function. Now, what is this operation here? And I want to find an operation that gives us exactly this expression. So I need, first of all, some kind of operator that extracts from the generating functional the, for example, physical density in configuration space of the particles that are represented by the generating function. So how do I do that? Well, first of all, since the density in our case at any position q and at time t is given by a collection of individual particles, I know that this density must be a sum over delta functions or delta distributions. I write it like this for all the particles here. All right. Now this, of course, so these particle trajectories here are functions of time, and thereby the density gets its time dependent. Now with this collection of delta functions, I can't do anything. It's a very unhandy way of representing this density. So I would go into Fourier space in order to calculate power spectra, and also because then all these delta distributions will turn just into Fourier phase vectors. So then I will get the Fourier transform density as a function of wave vector now, and a function of time. And if you Fourier transform the whole thing, then you see that this is the sum over Fourier phases. And you get e to the I plus or minus. You get a sum over phase vectors like that. I'm not sure whether it's plus or minus in the Fourier phase, depends on the Fourier convention. So our Fourier convention was that if you go back from configuration space to Fourier space, you have a negative sign in the phase factor. That was just by our convention. So I would have to have a negative sign here in order to stick with this Fourier convention. All right. It's normalized. Okay, yes. If you integrate over this, you get n, so you divide by wait a moment. No, because that is the Fourier convention I chose here. Okay, fine, but I'm ignoring this for now because I defined the integral over k such that the integral operator with a k as a subscript contains the 1 over 2 pi cube. So let me drop this for now, okay? So what I want to illustrate is just that first of all you get a density which is sum of delta distributions, then you carry this into Fourier space. Then the whole sum of Fourier phase factors here contain the positions of the particles. And now we need to have some way of extracting the particle positions from the generating function. Okay. And so I use the following method. I'm going to replace the particle positions qi by an operator extracting the particle position from the generating functional. And by definition of the generating functional, this is going to be minus I. And now the derivative with respect to the source field J. I'm here, right? I'm taking a derivative with respect to the source field J. Since the source field J is a function, I have to take a functional derivative. Then I'm pulling a factor of I down. This is why I multiply this with minus I. Then the function or the field J contains components for Q and P, but I only need the derivative with respect to the Q component of the field J. And then I need to do this for particle number I. That's what I'm going to do, right? I'm going to replace the particle position Q by a derivative with respect to the source field that takes down from the exponential factor here exactly the particle position that I was looking for. And in this way, the next step here, in this way I'm going to replace all the contributions here let me call that rho I of k and t, which means the contribution of particle I to the Fourier component at wave number k and time t to the density. I replace the rho tilde I of k and t by a density operator, a one particle density operator of k and t, and this density operator has the particle position replaced by the functional derivative here. All right, so I need to replace in the minus I k times q, the q with minus I times delta with respect to delta qi. So that's going to be minus k times delta j qi at time t. I should complete this. Right? So these are my one particle density operators. And now I know what to do. Now, in order to calculate correlation functions like this, I would apply sums over one particle density operators. And I would first of all get, because I have transformed the Fourier space, an R-point power spectrum. R-point spectrum. And then if I wanted, I could go back to configuration space by doing Fourier transform. So that's the logic of the complete procedure, right? We introduce the density as a sum over delta distributions. We transform the delta distributions into Fourier space in order to get something manageable. Then we have a sum of Fourier phase factors. In these Fourier phase factors, the particle positions occur. We replace the particle positions by suitable functional derivatives with respect to the source field J, and then get density operators. And we can apply these density operators to the generating functional. We would get average values exactly as you would do in ordinary thermodynamics with your partition sum. Right? For example, if you wanted to have a mean value in thermodynamics, you would take a derivative, ordinary derivative, with respect, for example, to the chemical potential, or the beta factor, or whatever you would like. You would get the average of the conjugate quantity. If you take a derivative with respect to the chemical potential, you would get the mean particle number. If you take a derivative with respect to beta or minus beta, you would get the mean temperature, and so on and so forth. So the procedure is exactly like in thermodynamics, except that we now need to have a functional derivative because we want to retain time information, because we have a non-equilibrium system. Right? So we need to take derivatives with respect to functions and therefore functional derivatives. But the logic is entirely the same. So what do we do here? What do we do here? We would calculate spectra like this, right? Correlation functions in Fourier space by applying density operators, as many as we need, to the generating functional as a function of the source field J. And once we are done, we would set the source field to 0. That's the procedure we have to apply. And very much of what we are going for the rest of this lecture, right, into February, will be to carry out operations like that. Okay, that's the goal. That's what we need to do. Now, several remarks. First of all, this is going to be an awkward sum over all particles, right? Sum over particle index 1, sum over particle index 2, sum over particle index r. So this would be sum over I1, I2 until IR, where I1 counts all the particles contributing to rho hat of 1, and so on and so forth. And then we would apply rho hat I1 of 1 So all of this is decomposed into an application of one particle density operators. We just need to sum over them. But all these particles are indistinguishable. So the result of applying any of these one particle density operators must not depend on the particle index. So I will get the same result for any value of IR minus 1 down to I1. In other words, by applying the first density operator, I will get n times the result of the particle, of the one particle operator applied to Z of J. By applying the second density operator, I will get n squared times the result of applying the one particle density operators to the generating function and so forth. So this is going to be n to the power of r times the application of all the one particle density operators. But now, since the particles are indistinguishable, I can enumerate them as I like. So I can write particle indices 1 to r instead of particle indices I1 to IR. Right? Because I can enumerate them to my liking. Okay, apply to set of J and setting J equals 0 at the end. Okay, so we need to work out what it means to apply a single one particle density operator to the generating function in the first place. So that's going to be the exponential of minus some k vector. Let's take the first one, right, of the first density operator here, times delta J Q1 at time t1. Right? If t1 is the time when the density operator acts, yes.
Usually when we write on an answer like this, to fully make sense of it, we take the version by essence of series of information. So when we generally write down something like this, we get the diversion theory. Only if we have some control parameter, maybe like this number of field components, like in large NX function, then we can properly resum and make sense of it.
I think so, but I don't know. I mean, what we are assuming here that we have a very large but finite number of particles. And we also have a large, or possibly large but finite number of density operators applied. So we have to do with finite operations here. All right, so we need to know what is this, right? What is the exponential of the derivative? And it's going to be a very simple result. And I'm going to sketch this on the other board here. Let me sketch this over there. So suppose you want to know you have a function f of x, and you want to know what is the function f taken at x plus dx. You do something like this. Taylor's theorem, first order approximation. And as long as dx will be small, that's going to be a nice thing. And you can write this in operator form as this, right? You have an operator which is 1 plus dx times the derivative with respect to x applied to the function x. Not surprising, is it? Now, you want to evaluate the function f of x plus y. So now you want to have a finite translation by y. And you divide y into n steps, where n is a very large number, and you carry out the same operation n times. In other words, you use this infinitesimal translation operator here as the generator of finite translation. And then you get 1 plus y divided by n times dx taken to the power of n applied to x, and you take the limit n to infinity. And then you recall that this is an exponential function. Right, so in the limit of n to infinity, this is e to the power of y dx applied to f of x. Yes?
But in order for this to make sense, you would, like, if y isn't very big, then it's fine. But when you do the first step, right, then you take the derivative with respect to the starting position, but that gets translated all the time. So it's like
that's contained in this operation here. So what this means is that derivatives are the generators of translation. And you know this from quantum mechanics, for example. Right? The momentum operator is a derivative, and it generates spatial translations, as you know from Noether's theorem. So we're just using this backwards. We have an exponential of a derivative. Here it's a functional derivative, but so be it. And then we know what this means, right? It's just going to create a shift. So, in other words, if I apply this operation to the generating functional, and then set j to 0, it's going to replace the argument of the generating functional by a shift. I call this shift L. So that's going to be set of L, and we have to work out the L. All right. Again, so what I'm using is that, first of all, in Fourier space, I know that these density operators contain exponentials of derivatives, but an exponential of derivatives of a derivative creates a shift. And so what I know is that once I have applied a density operator to the generating functional set j to 0, I'm going to get the generating functional at the shift L. Now we have to work out the shift. That's going to be minus k1 times the application of the jq at time t derivative to this phase vector here. So the L is going to be minus k1 times delta taken with respect to, let me just copy this here, q1 of t1 apply to the scalar product here, right? Because I know that the exponential is just going to be returned by the functional derivative, and then I have to take the internal derivative into account. Let me write that this will be L times, this will be the shift L times X. Right? Or if I want to have the shift alone, I would have to take the functional derivative of the source field J of some general time t with respect to these components here. Now let me generalize this and say, okay, I'm going to apply this for particle I, and now I need to take this functional derivative here. It's going to be minus ki times. All right, now first of all I have to take the functional derivative of j of t with respect to j of t1. That's going to give me a delta function, delta distribution in t minus t1. Then I have to take the functional derivative of the complete of all 6 components of the j field here with respect to the q component. That's going to give me a finite result if I hit the first 3 components of q, and 0 if I hit the second 3, so momentum components of the j field. Then it's going to give me a delta, a Kronecker delta, but that I have to explain in more detail. So remember, j of t can be written in this way. This complete bundle of source fields for all the particles together. So it's summed over EI. All the j fields for any particle have 6 components, 3 for q, 3 for p, and I need to take the tensor product over these unit vectors EI to get the complete structure for all the particles together. Now let me replace this index here by j, and again take the functional derivative with respect to jqi of t1. Then first of all, you will see it's 1 here, and it's 0 here, times delta ij. Times ej, and then I get the delta function from the functional derivative with respect to the time t1. So this is what I will get. And this is minus the wave vector ki times the delta distribution times 1, 0, and then the tensor product with EI to identify the particle. Yes.
Don't have a different text for not
Well, but I can renumber the particle such that it is, and that's what I'm doing. It's true that I should start with indices I1 to IR, but then I can enumerate the particles as I like. All right, so that's the shift vector L, where we now have to evaluate the generating function. Okay. The logic is really straightforward. We see that we need to extract particle positions from the generating functional in order to calculate densities. We extract the particle positions by functional derivatives with respect to the source field. We have to have functional derivatives because we want to retain information about time. Then because we transformed the delta distributions that constitute density into Fourier space, we get these derivatives in the exponential. derivatives in an exponential are finite translation, and we just calculate by how much the generating functional is being translated here. And that spatial derivative gives you finite translations, is known to you from the momentum operator, for example, or from classical mechanics already. Right? The same reason why in the position representation in quantum mechanics, the momentum operator is a derivative. Okay, so now we know the shift, and we know the form of our generating functional. So now we can simply insert this result into the generating functional. And of course, what I should also say is that this is now the result of applying a single density, single one particle density operator. Now, of course, if you do this multiple times, you get the sum of shifts for all the particles. All right. So this means that if you apply the same operation to all the R density operators that we have applied, we get our spectra, R point spectra, just as Z of L. And that's it. And we know what the L is like. The L is minus the sum over all density operators applied, Ki times this thing here, right? The delta distribution to pick out the right time, the 1,0 vector to pick out the right component, and the tensor product with EI to pick out the right particle. That's it. Now you see, this is the result for a single one particle density operator. So we get a factor of n to the power of r up front. Because the particles are all indistinguishable. And so we know what this is. This is n to the power of r, integral over the initial conditions. Now, exponential of I times L times x bar. Well, let me write it like this. But of course, now the time integral that is still contained in this scalar product here will all return the particle positions at the times when the operator is going to be applied, and the time integrals are going to disappear. But that is it, right? This is all we have to calculate now. No more, no less. Now let me go a little bit, or yeah, do you have questions so far? I hope, yeah. Well, this is meant to be a collection of 3 ones here. This is meant to be a collection of 3 zeros here. So when you multiply this with k, well, you get the same as you say. Let me go one step further, and then I think it's going to be more clear. What I want to bring across with this calculation is not exactly that you follow all the steps of the calculation right away, but that you follow the logic. Right? And the logic is in fact really straightforward. Right? You have delta distributions, you bring them into Fourier space, you get exponentials of derivatives, those create shifts, the shift is this expression. The G are power spectra now. Yeah. Did you show up? Yeah.
So we went from a full phase state to a selection of particles. That's because we identified with the phase we are now talking about as a non-trivial topology.
All right, yeah. We have a rather complicated space consisting of the trajectories of n particles now. All right. But you see, this is charming, isn't it? I mean, you just have to integrate over an exponential function. All right. Let's go a little bit further here and see what happens if we calculate this scalar product here. And what I want to do now is I want to insert free trajectories only and leave the question of particle interactions aside. Right, so for now, I'm going to exclude particle interactions. This is why I'm adding a subscript 0 here now. And this will be the Green's function of t and 0 applied to the initial particle positions in phase space. And the Green's function, you know, right? This is a 6 by 6 matrix for all the particles. So I can write the Green's function for all particles together in this way. And the G of t and 0 is just given by this beautiful object here. Right? Provided we use the Seldovic trajectories as reference trajectories such that our time coordinate, which is in fact the linear growth factor, appears in the Green's function exclusively. Okay. So this is an integral from 0 to t over dt prime. Now the shift vector, which is in fact a tensor product here, evaluated at t prime. Now the ordinary scalar product of this with g of t and 0 times x initial, t prime and 0. All right, now in order to evaluate this complete expression here, we can split L up into one particle contribution and first have a look at what this expression means for a single density operator or for a single particle contribution here. So let me do this first, and then we can easily assemble the rest. So let me pick out any of these contributions to the L tensor, the wave vector Ki times a delta distribution in time times the 1, 0 vector that picks out the right component. Tensor multiplied with EI to pick out the right particle. This is just, of course, one section of the L shift. Now I need to take the ordinary scalar product with the Green's function, which is the same for all the particles. It's the complete Green's function structure that I have. And this is multiplied by the initial phase space position of particle number j times Ej for all the particles. All right, so here I have a huge matrix expression, just multiplied with this huge vector here. And then to this complete vector that comes out from this multiplication, I have to multiply this vector here in a scalar fashion. All right, so the first thing will be that we have to apply this matrix Green's function here to this phase space position here, which gives you Qji plus T prime Eji. If I multiply this with that, then I get Pji. This is now the result of multiplying this matrix with this phase space position. Of course, gives you the evolved position of particle number j. Then I need to take the tensor product of the result of applying this unit matrix here to this vector Ej, which is of course Ej. Okay, now I can multiply everything together. Now, but first of all, you see you get an Ej times an Ei times an Ej. This is your Kronecker delta, delta Ij. Then you have this vector 1, 0 in a scalar multiplication with this vector that just picks you out the first, or the spatial component of this. And then you multiply, as you said, the wave vector here times the scalar, the component in Fourier space. So this is going to be minus vector ki, scalar multiplication with Qji plus T prime Pji. So here we just multiply with the particle position the wave vector k, right? That's what comes out from our Fourier phase that appears in the delta distribution. And then we have delta Ij. Yeah, that's it, right? So that's going to be times times the Dirac delta. So this is going to be minus ki qi initial plus t prime pi initial. That's an ordinary scalar multiplication. Then times this here. Yes, thank you. And now you integrate over this. You integrate the whole ordinary scalar product over time, and all the delta distributions drop out again. And then you can bundle those parts of this expression that you multiply with the positions q, and those parts of this expression that you multiply with the momenta p, and write the whole thing in the following way. LQ times Q plus LP times P. And the LQ is now minus the sum over all density operators applied, Ki vector times EI. This gives you, after the integration over time, this part of the expression here. And the LP is going to be minus sum over I equals 1 to R, Ti, Ki, tensor EI. So I just separate the two shift. I separate the total shift vector into two contributions that I can separately multiply with the initial positions Qi and the initial momenta. All right? The notation is uncommon, I know, but the idea, I think, is very clear. So now I can insert this expression here into the generating functional. And then we can even integrate further. Okay, so now we get an expression for our R point spectrum, which is going to be n to the power of R integral. I'm going to write this integral measure out. Integral dq dp. Now the probability distribution for the momenta a normalization factor now. This is just another word of saying d gamma. Now we are here. Now we need these factors here. I'm going to write them as this. So it's e to the power of I LQ times Q initial plus LP times P initial. And let me now drop the superscript I, because now all the Q's and P's that appear in this equation are Q's and P's at the initial slice through phase space. Yes? What do we have to do? V to the I understood e to the minus n. I was completely confused. You're right. That's true. That's true. Yes, to normalize the spatial distribution. Yeah. Okay, but look, this is a Gaussian integral in the momenta, right? And this is the main reason why I wrote these shifts in separate LQ and LP components, right? Because now you can immediately carry out the momentum integration. It's a Fourier transform of a Gaussian in the momenta. So we can completely integrate out the momentum contribution now. And this means that the normalization factor will be gone except for the v to the minus n, right? Because that goes away by the Gaussian integral. It will replace the p by the LP, and will replace the CPP to the minus 1 by CPP. just the Fourier transform of a Gaussian. So this is going to be n to the power of r divided by v to the power of n. And now all that remains are the q integrals only of exponential minus a half LP transpose CPP LP e to the I LQ times q. That's it. So now, depending on the correlation structure of the particle ensemble in momentum space, this can be a nightmare to calculate or can be easy. Suppose you have an ideal gas. Suppose you have an ideal gas, then of course all the momenta are uncorrelated. Then the CPP would just be a measure of temperature and would be completely diagonal, and all diagonal elements would be the same. Right? Because the same temperature of the ideal gas would characterize all the momentum variances, and there are no cross correlations between momenta. Then you would get a measure for the temperature here, and then you would have a unit matrix. Then you would have LP times LP, so LP squared. But these would not depend on spatial coordinates any longer. So you could take the complete exponential out of the integral. Then you would have an integral over dq over this phase factor here, which would give you all delta functions of LQ. This would set all the wave vectors to 0. This would set all the LPs to 0. And the whole thing would be that your power spectrum would just be a constant, as it should be. That's the easy case. Now, the CPPs will in general be dependent on spatial positions, and then of course things become more difficult. Nonetheless, there is one more thing to observe here. In the LQ, you only have R components, where R is the number of density operators that you have applied. Right? There's a sum from 1 to R contain contributions for the first R particles, but then particles from R plus 1 to N are unpaired here. They also, so the positions of particles R plus 1 to N do not appear in this expression either anymore. So this means that we can immediately integrate out particle positions R plus 1 to N. That's one thing. Then we will get a factor of V to the power of N minus R from these integrations. And we would have to integrate over the remaining particle positions 1 to R only. Of these R spatial integrals, we can also carry out 1, because the whole structure must not depend on absolute position, because we have assumed a homogeneous random field. So the origin of the coordinate system is entirely our choice. So let's put the origin of the coordinate system on particle number 1. Why not, right? Then, because we have a homogeneous random field, all the correlations must not depend on the absolute value of Q1. Right? They can only depend on the relative positions Q2 minus Q1, Q3 minus Q1, Q17 minus Q95, for example. But certainly not on the absolute value of Q1. Then we can subtract Q1 out of this here, and we get a delta function of the respective LQ. We can carry out the Q1 integration as well. So if we do all of that, only R minus 1 integrations over Q's remain. And all the rest is gone down the drain. Okay. Before I do that, let me write this in a somewhat different fashion here. Let me write I want to do something like this, right? I want to subtract Q1 from all of these particles. But now I have to be careful, right? I want to subtract from all the particle positions that are contained in this tensor structure here. I want to subtract Q1, so I have to subtract the sum over Q1 times EI from I equals 2 to n. Okay, this is just saying all the particles get reduced by Q1. Let me call this R. Right? These are all the relative coordinates of the particles referred to particle position number 1. And then, of course, I have to write, instead of this is LQ times R. Okay, but now plus LQ times sum from I equals 2 to n Q1 times EI. All right. You see what I'm doing, right? I'm just subtracting Q1 from all the particle positions, and then I'm integrating. I'm going to integrate over Q1. And according to this is giving me a delta distribution of LQ. So this is going to be an integral over rho bar to the power of R, where rho bar is the mean density. Right? It's just the number of particles divided by the volume. Because, as I said before, right, n minus r of these factors v to the power of n is going to disappear. Then I have n to the power of r divided by v to the power of r. That's the mean density to the power of r. Then I get 2 pi cubed delta d of LQ. This is again a delta function which is a consequence of the random field being homogeneous, as we saw when we talked about power spectra. Right? And then what remains is an integral over the remaining r minus 1 particle positions, which are now taken relative to particle number 1. And then we have e to the minus a half LP transpose CPP LP times the Fourier phase factor, which is now an LQ times R, because we have integrated out particle position number 1. Okay. Again, the logic is really, really simple. All the density operators give you a shift. We insert the shift instead of the source field J. We split the shift into a shift in position in momentum space. We see that we can integrate out momentum space completely. Of the remaining spatial integrals, we can carry out n minus r plus 1. So r minus 1 integrals over spatial coordinates remain. So for example, if you wanted to calculate a 2-point spectrum, right, an ordinary power spectrum, r would be 2 and a single spatial integral would remain. seems manageable. And then we have a Gaussian in the LPs, and we have to back transform. It's just a Fourier transform. We just have to back transform this Gaussian here. And the main difficulty is hidden because the covariance matrix here depends on all the spatial positions. So that's where we have to stop for now in order to carry these things out. But that is the main result for the moment, right? And let me. So many boards here. Yes.
Because R is the direction in which the integral we had right at the beginning. R is the principal exponent, right? It's the same R.
No.
So what is it?
R is just the vector of relative coordinates. So.
Yes, it's the one that we had right at the beginning where we had the integral over K, and it was the one that signified the principal axis.
Where is the principal axis here? Yeah, purposefully. So for now, I mean this structure here. Now it has components of which the R that I used before is just one element. Okay? But I know it's confusing because here's another R. But I wanted to have the R because it's a relative coordinate with respect to Q1. Okay. So this is the main thing for now. We have a general expression for the free, because we have ignored interactions, right? For the free R point spectrum. Contains a beautiful delta distribution here, which already contains the sum over all k vectors that we need to have here. Okay, yes. Then we have rho bar to the power of R. Now an integral over the remaining relative particle contributions. Gaussian times the Fourier factor. Okay. Suppose you apply one density operator. There is no integral left. There's just one contribution in this delta function. So you get a delta distribution at k equals 0, which is a constant. And in our case, the constant is just the mean density. No big surprise, right? Just to be reassuring. Okay, yeah. You will find more games on the problem sheet. But now let's continue a little bit more and take care of this quadratic form that appears in here, LP transpose times CPP times LP. Because we can further beautifullize this. We can work this out. Because we know what CPP is, we can use this knowledge in order to work out this quadratic form. So what's the goal now? The goal now is to work out this thing, knowing what LP and what CPP are. Yes. CPP. That's a structure that contains all the correlation matrices, the covariance matrices of all the momenta. What was that like? Well, that would be this beautiful thing. So it's a covariance matrix between any pair of particle momenta attached to the location of this pair in the whole structure of n by n particles. This is identified by this matrix here, which I called Eij before. And maybe let's emphasize here that this is sum over all I and j here. Now it turns out to be most helpful to split this whole expression into a contribution which comes from equal indices and a contribution that comes from different indices. So let me write, it's going to be the sum over all I equals 1 to how many? To n. Not a really nice abbreviation, I know, but these are the equal ones. And there are the different ones. Okay, now the reason why I'm doing this is because here two equal momenta are, two momenta at the same position are being correlated. That's how it is, right? Now, if this is the case, what's the difference between two identical positions? So we just have to evaluate these correlation functions A1 and A2 that I introduced last time at separation 0. It's going to be sigma 1 squared divided by 3, and I'm going to define these quantities right away. And this is 0 here. Yes. Doesn't matter because we evaluated at 0. You can do it the other way around and first say, okay, I'm taking the limit of this for r to 0, and then you see that this drops out. So that's what remains. Now, let me write down what I mean with the sigmas. So I'm using the general definition that sigma n square is 1 over 2 pi squared integral dk from 0 to infinity over k to the power of 2n minus 2 times p delta of k. It's just a definition, right? But if you look at a1 of r, this is minus 1 over 2 pi square integral 0 to k p delta of k j1 of kr divided by kr. This is going to a 1/3 for r to 0. then what remains is this expression alone. So you have 2n minus 2 equals 0, so n equals 1. So that turns into minus a third sigma 1 squared here. So this is plus sigma 1 over 3 times 1 times the unit matrix. All right, so you get the same contribution for all the particles, for all the particles I. And EII is a matrix that has zeros everywhere, but only on the diagonal at the ith place, there's a 1. But now you sum over all of them, so you get a unit matrix. And all these unit matrices have the same amplitude. So this is going to be sigma 1 squared divided by 3 times the unit matrix in n dimensions. This is the reason why it is advantageous to split off the equal particle contribution here, and then we have different particle contribution. And okay, let me write this out. This is going to be some, no, let me not write this out, plus CP IPJ EIJ, and here is a sum over I different j. So these are cross correlations of different momenta. These are autocorrelations of the same momenta. Now, once we are equipped with this beautiful knowledge, we can move ahead. Move ahead and calculate, first of all, the product of CPP with LP. So this is going to be sigma 1 squared divided by 3 times the unit matrix in n dimensions here. And then plus. Now let me write the EIJ matrix as it is, right? The tensor product of EI with EJ. This was, of course, too simplistic. Because this is sigma 1 squared over 3 for all three components of the momenta for all possible particles. That's how it should have been. Also up there, right? Sorry. Okay. Now this is the complete matrix here. Now we have to multiply this with LP, and the LP is given by minus the sum from k equals 1 to r over kk tk tensor ek. So how do we work this out? Well, first of all, we have a unit matrix in 3 by n dimension, 3 times n dimension. That is multiplied with the LP. That just gives you an LP back. So we have sigma 1 squared divided by 3 times LP. Okay, what happens here is that you get minus this 3 by 3 matrix times each of these 3 vectors. So it's a sum over k equals 1 to r, CPI pj times vector kk times time tk. You see that's a 3 by 3 matrix times a 3 vector. Just gives you a 3 vector here. Now what do you have? We have the matrix EI vector, EI tensor EJ. You have to multiply with a vector EK, that gives you a delta JK times the vector EI. So that gives you EI delta JK. And again, of course, we also have to sum over I different from J. But now the delta JK just reduces this sum here dramatically. And let me write this down in the following way. This is going to be sigma 1 squared over 3 times LP minus now the sum still over all particles I equals 1 to n. But the sum over J is now dramatically reduced. So the sum over K equals 1 to R remain. And then we have CPI PK KK TK times EI. Okay? Right, now we can multiply with LP transpose from the left. Huh? I should have I different from K, that's true. True. Okay. So now finally we need to multiply with LP transpose from the left. This is easy with the first term. This gives you a sigma 1 squared divided by 3 LP squared. This is a really troubling term. We'll see why. Then I get plus, right? Because the LP transpose here contains another minus sign, and it will give you a plus here. Sum of S equals 1, no, L equals 1 to R, KL, PL, A, tensor EL, transpose. That's the LP transpose with a minus sign. Then we have sum over AI different from K, sum over OK, CPI, PK, PK, KK, Here we have an EL applied to an EI. You see a delta Li. And with that, the sum over L is already gone again. And we have plus. The L's are now I's, right? Because this EL times EI gives a delta delta IL. So we have KI, PI, CPI, PK, transpose, sorry, KK times PK. Now, now I'm using Einstein's sum convention again that over I and K needs to be summed. Yes.
One question: are there cross
Yes. All right. So you see, this is now sigma 1 squared divided by 3 LP squared plus TI TK. These are the two time factors. I'm going to lose one more word about these, and then we just have vector KI transposed CPI PK KK. Now, usually you want to have synchronous power spectra, where all the density operators apply at the same time. Then this, let's call this time T1. Then this just gives you a T1 squared. And we could go even further, right? Because we know what these things are. They are minus A1 times the unit matrix minus A2 times the parallel projector. This, of course, is independent of the particular pair of particles that you have chosen, but the parallel projector now, of course, is one that applies for each pair separately. All right, so you could go on to write sigma 1 squared divided by 3 LP squared. Let me do this now and suppose that we want to have synchronous power spectra. There's only one instant of time, call this T1. Then you have minus A1 Ki times Kk. It's just the ordinary scalar product of the two wave vectors. And then we have minus A2 Ki pi parallel Ik times Kk. And this, of course, now depends on the orientation of the separation of the particle pair between the particle pair Ik relative to the wave vector here. But this is now the simplest form that we can have. Suppose we want to have a power spectrum of order 2, then we have just two wave vectors here, K1 and K2, but we know from the preceding delta function that K2 must be minus K1, so this would be just A1 times K1 squared. Then we only have a single particle pair, and we project the same wave vector on the orientation of the separation between these two particles. This gives you a cosine square of this angle between the separation vector and the wave vector. And then you can very easily carry out the one remaining spatial integral. But so far so good, right? This is where I wanted to arrive. Right? This is about as far as we can break down the remaining quadratic form that appears in this expression here. So what have we gained? We now have an analytic expression for the R point spectrum. Where R is arbitrary for a free particle system, right? We have so far ignored particle interactions. How we can take them into account is a different business, but we have achieved already quite a lot. We know how to calculate R point spectra now in a free particle system. Do you have questions? Other than when does this end? Then it's ending now. Thank you.
Eine Frage.
Mhm.
Wir sind jetzt aber immer noch an dem Punkt, dass wir dort reingesteckt haben, dass die Friedmann-Metrik auf einen Skalen eine gute Näherung ist. Oder? Da sind wir immer.
Also wir verhalten uns so, als könnten wir Hintergrund und Störungen voneinander trennen, so dass wir die
Quasi ein Phi im Hintergrund und die Teilchen im Vordergrund.
ja und die Bewegung des Hintergrunds ist die reine halbe Bewegung. Also die freie Fallbewegung auf dem glatten Hintergrund.
Aber ist das noch eine gute Näherung für alle Strukturen? Denn ich meine, wenn wir uns sowas wie die Airline angucken, ist es schon nicht mehr der expandierende Hintergrund, der eine gute Näherung ist, oder? Sondern es ist eigentlich schon eher 3,1.